talk. So I think with this, folks, I'll just remind you that this seminar takes place every Friday at noon Eastern Time. This video will be recorded, but you can only ask questions now. Subscribe to the Qiskit YouTube channel to go back and see previous videos and hear about new ones coming up. And so I think with that, without further ado, I think it's time we begin. Today, I'm thrilled to roll out the latest and I think final for the year episode of the IBM Qiskit Live Quantum Seminar Series dedicated to you, the research and academic communities. I'm your host, Latko Minev from IBM Quantum Research, and I have the pleasure of having Andrea Mari from the Unitary Fund here today. Hello, Andrea. How are you?
Hello, Zlatko. Hi, I'm fine, and I'm very happy to give this presentation at this Qiskit Seminar Series.
I'm delighted. We also have some folks that I recognize tuning in from Italy as well, and I believe you're in Italy now. Is that right, Andrea?
Exactly. Yes, I'm tuning from Italy.
All right. Well, buongiorno and buonasera to Nathan and everyone tuning in. Before we pull up your slides, Andrea, allow me to give a bit of background. Andrea Mari received his PhD in physics from the University of Potsdam, Germany. Andrea has been a postdoctoral researcher in quantum information theory at Scuola Normale Superiore, Pisa, and CNR Nano Pisa for 6 years. From 2019 to 2020, Andrea worked at Xanadu on quantum machine learning, and since 2020, he's a member of the technical staff at Unitary Fund. And hello to all of you Unitary Fund folks here in the chat today. With that, Andrea, the stage is yours.
So thank you very much for the nice introduction and for hosting this presentation. So what I would like to speak about is a general introduction about digital error mitigation, in particular with Mitiq, which is a software library developed in Python that can be used to apply error mitigation to quantum programs. So Mitiq is a software library which is open source. The repository can be found at this link, and has been developed within the Unitary Fund organization, which is a non-profit organization working in the field of quantum computing and quantum technology. So before starting, I would like to thank all the people that you see here, Ryan, Sarah, Peter, Nathan, and Will, which are members of the Unitary Fund, but also a lot of independent GitHub contributors that you can see here highlighted in green. And actually, this list is not complete. These are just the authors of the white paper of Mitiq that you can find on the archive at this link. But if you want to see all the contributors of Mitiq, you can check the repository that contains all the information. So with this, I would like to start with the outline, which is the following. I would like to start with an overview explaining what error mitigation is, if you don't know what we are talking about. Then I will give an overview of Mitiq, focusing on the three main modules which correspond to different error mitigation techniques. The first is zero noise extrapolation, the second is probabilistic error cancellation, and the third is Clifford data regression. And at the second part of the slides, I would like also to highlight how Mitiq can be used also to test new research ideas. So it's a toolkit that can be useful also at the research levels, when, for example, an error mitigation technique is still unknown and unexplored, but can be tested using the tools of Mitiq. And finally, I would like to show a notebook in which Mitiq is used in practice with Qiskit circuits. So actually, you can find this link of the notebook in the description of the YouTube talk that you are seeing. And so if you want, while I'm speaking, you can already click on it and download and load it and maybe later we can try to code together to see if it works also for you. So now let me start with what is quantum error mitigation. So the best way to understand error mitigation is to compare it with standard quantum error correction. So in standard quantum error correction, one typically encodes logical qubits into many physical qubits, then performs intermediate measurements to detect errors, and finally, actually, as soon as you detect an error, you apply a recovery operation. So this is very nice because it's scalable. In principle, you can obtain a fault-tolerant quantum computer in this way. This is a very important and actually well-established result of quantum information theory. On the other hand, it's very hard to apply with near-term quantum computers because it requires a lot of qubits and classical control. What is instead very easy to apply with the computers that we have today is error mitigation, which can be considered as a kind of compromise between not applying error correction at all and the ultimate goal of error correction. So in error mitigation, actually, instead of correcting errors as soon as they happen during the computation, what you can do is that you run a set of multiple and different noisy quantum computations, which are related to the computation that you want to implement. Then you collect all the results, and then you infer, given all the noisy results, what could be the ideal result that you want to extract. And this is, unfortunately, asymptotically not scalable in the sense that at some point, for very long circuits and large number of qubits, the cost of error mitigation is exponential. But for near-term quantum computers, it can be still very, very useful and give a good reduction of the error. So basically, Mitiq is a Python library that is open source. It can be used together with other quantum software frameworks exactly to apply such error mitigation techniques. So the scope is this, and Mitiq is compatible with a lot of quantum software libraries like Cirq, Qiskit, PyQuil, Bracket, and Penny Lane. And it is structurally designed to be backend independent. This is a very important point that I will explain better in the next slides. So in order to understand what is the main idea of Mitiq, let's consider a typical workflow that you have usually when you use any quantum software library. So for example, you may use Qiskit, Cirq, PyQuil, Bracket, Penny Lane. In all these cases, you usually write down a quantum program that you then send to a backend, which can be an IBM device, a Rigetti device, IonQ, Amazon, or it could also be a simulator. And after you get this, you get back a noisy expectation value. And actually, this is the workflow that we aim to mitigate. So it is important that we are speaking about expectation values because error mitigation works and can be applied only to those computations in which the output is an expectation value. And actually, a lot of near-term algorithms are based on estimation of expectation values. So this is a restriction, but quite useful scenario. So the main scope of Mitiq is to act as a thin layer between the user and the hardware. So in some sense, it behaves as a kind of compiler between the user and the hardware. And the two main tasks that are performed by Mitiq are the following two. In the first step, a quantum program which is written by the user is compiled into a set of intermediate programs, which usually are a set of intermediate quantum circuits. And depending on the error mitigation technique, zero noise extrapolation, PEC, and so on, the set of circuits that are generated will be different. And these circuits are then executing on the hardware. And as you can see, the hardware doesn't live inside the space of Mitiq. So these circuits are basically executed by a black box, which is the hardware, which is defined by the user. And then all the noisy results are sent back to Mitiq that will combine all these noisy results to get an inference, basically a guess of an error mitigated expectation value. So let's see how this framework can be used to apply zero noise extrapolation. So zero noise extrapolation, first let me explain what it is. So it's a very intuitive way of reducing the noise of a computation. So imagine that you plot in this diagram the value of an expectation value on the y-axis and the level of noise on the x-axis. Actually, we call this lambda. And we normalize the noise such that when lambda is equal to 1, we are actually executing the circuit at the hardware noise. And so if we measure an expectation value, we get a point at this lambda equal 1 axis. What we would like to know is the value of the expectation value at lambda equals 0, because it is the zero noise limit. But unfortunately, of course, we cannot measure this value. What can be done is to increase the level of the noise to larger values of lambda, to take basically different measurements with different lambda. And then when you have all these blue points, you can fit a model. In this case, it's an exponential fit, and extrapolate to the zero noise limit. This will be the error mitigated expectation value. And as you can understand from this plot, there are two main requirements to do this. You first need to scale the noise in some way, because it's not so trivial to increase the noise of a computation. And also you need to decide which kind of model you want to fit to your data. And basically these two steps correspond exactly to the two main steps that I've shown you before in the general workflow of Mitiq. So to apply this, Mitiq compiles the input circuit into a set of noise scale circuits, and I will explain soon how this can be done. These circuits are executed on the hardware. The measurement results are collected. These are all the blue points that we have seen before. And depending on the extrapolation model, you get an error mitigated expectation value. So how can we generate noise scaled circuits? So we want to scale the noise. What does it mean to scale the noise of a circuit using a compilation approach? So actually one of the first way in which noise was proposed to be scaled was in this paper by Temme, Bravi, and Gambetta. They are IBM researchers. And they proposed a very nice trick, which is you take a circuit and you just apply the same circuit, but stretched along a larger amount of time. So you just take the physical pulses that you send to the qubit and you stretch them in time. In this way, you get the same, in principle, the same circuit, but since you are applying a longer computation, you are actually increasing the effective noise that acts on the circuit. And this can be considered as an analog way of stretching the circuit. In principle, you can also do this in a digital way. So without acting on the physical control pulses, you can try to increase the effective length of the circuit by compiling the input circuit with a larger number of gates. And the techniques that are used mainly in Mitiq are these two. The first is called local folding, and the second is global folding. So in local folding, each gate G is replaced by G dagger G. And since G dagger G is the identity, basically you are, in principle, if you have an ideal simulator, you are doing nothing to the circuit. But in practice, if you use a real device, you are increasing the noise. And in a very similar way, you can apply global folding, which means that now you apply this trick to the full circuit, or at least to a full set of layers of the circuit. And again, in the same way as before, you increase the effective length of the circuit. And so you increase the effect of gate errors in the computation. So this is...
Yeah, this is really nice. Just skip. Would you take a couple questions on local versus global folding?
Yes.
So with global folding, you have your global circuit has to be the identity. So you can only apply that to certain circuits. Is that right?
Actually...
or well, I guess, sorry, maybe I misspoke. Yes, if you can do the inverse. Yes.
Exactly. So what is the identity is G dagger G. And you are left with your original circuit.
Yeah, that's right. And can you say a little bit more on kind of the how important is the way in which you scale between these, because they're not probably going to lead to the same type of effective lambdas and scaling as if you were stretching the gates. Do you know if people have looked at that and how important that is, or how that affects parameters?
Yeah, so this is still a matter of research, but we have experiments in which both techniques have been applied, and they seem to more or less agree and work for zero noise extrapolation. But what is better, what is optimal, we also don't know exactly. It's we are working on this, but it's an open question.
Mm-hmm.
And yeah, I will show experiments in the next slides.
Okay, great. Yeah, maybe I'll hold off there.
Okay. So just to give a practical example, if you want to do this with Qiskit, assume that you define a very simple circuit, Hadamard followed by a control knot. You can simply now call these functions, which are called global folding, for example, and you apply it. You can choose the scale factor. In this case is 3. And what you get is a new circuit equivalent to the original one, but with 3 times more gates than the original one. And this is the simplest case, but in principle, these functions are defined to work also with intermediate values of lambda, not just integers, not just odd integers, but even any arbitrary real number larger than 1. And once you have this, basically, you can apply the first part of zero noise extrapolation. Then you execute all these circuits, and we are still back to the problem of the inference. How can we extrapolate to the zero noise limit? And again, this is also, there are different methods to do this, and they are, some of them are built in Mitiq. For example, you can use linear extrapolation, Richardson extrapolation, polynomial, exponential, even adaptive algorithms. And all these methods can be encapsulated, so can be defined by individual factory objects. So we have a class for this, which is the factory class, and each factory can represent a different extrapolation method. And this is the experiment that I was speaking before, in which we used a randomized benchmarking circuit executed on IBM hardware and also on Rigetti hardware, in which we scale the noise using unitary folding, and we use different inference models to understand which one is better for this kind of device. And actually, what we found is that, yeah, usually the exponential one makes sense, especially if you expect an exponential decay like this. It's not always the case. So sometimes it's better to use linear, extrapolation, polynomial, and so on, as shown, for example, this example here. So I guess this is a quick overview of zero noise extrapolation.
Can I ask
And
you a
unless you
couple
have
questions
questions, yes.
could you tell us about the error bars? What are those here? What do they?
Yeah, so if I remember correctly, we probably we have a statistical uncertainty for each point, which is due to the random to the statistical uncertainty of random of quantum measurements, because we are using a finite number of shots, and probably in this case we were also generating different circuits, random circuits, and averaging over several random circuits. I think I need to check back on the paper, but it's basically a statistical error on the blue points. And on these extrapolations, you also get an error, because if these points are not precise, the fit will have an intrinsic error also, and so the extrapolation too.
Yeah, I think the fit one I understand. Maybe the raw data one, I was wondering how you obtain those, with like whether it's bootstrap, because you have both number of shots and number of randoms, a number of yeah. So by the way, the one more question that popped up, maybe I think it was on the previous slide, was how can you have a fractional scale factor, like half a gate?
Yeah, that's a good question. So the trick is that usually you have a much longer circuit. You don't have just two gates. Assume that you have 100 gates. Then you can apply unitary folding not to all the gates, but to a subset of the gates. And depending on how many gates you select to apply unitary folding, you can approximate any real number larger than 1. Of course, it's a rational approximation, so it's not exact. But if you have a circuit of sufficiently many gates, this becomes exact.
So you basically use a subset of the gates and extend those gates, right? So that would
Exactly.
mean that you're sort of only, so some of your noise would remain, um, basically, let's say you have one really, really bad gate, which you don't include in that subset, then you're not scaling that one really, really bad gate, right? Because you could have picked the gates that are really, really good. And so your scaling wouldn't really allow you to invert that one particularly bad gate. Is that right?
Yeah, that's a problem, but in principle, you can do two things. The first thing is that you can apply it. There is a way in Mitiq in which you can select the gates which are more noisy. Usually you know what are the gates that are more noisy, for example, control nodes. And then you can apply unitary folding only to control nodes, if this is the problem. Or another useful way to avoid this problem is to randomize this effect. So you can apply a function which is called random local unitary folding, which basically select at random which gates to fold. And if you repeat the experiments with different random seeds, you are averaging over, and so you more or less you get on average a good sampling of the error in your circuits.
And yeah, I see. And calculating, I see. And I guess for you, calculating the G dagger is pretty easy?
Yeah, because it's just, it's a local problem. So you have a gate here, you apply the inverse, and you apply the inverse of the gate. It's the kind of reverse gate, the reverse circuit, right? It's not a computationally hard problem.
Great. Okay. I think we've got the questions. Oh, maybe one question just came in. Let's see. For
Yes.
different state expectations, do you need to use different inference models? For example, oops, and I lost the question. For example, will the expectation value of 0, 0, p 0 and yeah, basically depending on the expectation value, do you have to use potentially a different model, whether it's linear or so forth?
Yeah, in principle, the same model should work with different expectation values, because the noise here is acting on the circuit that prepares the final state before measuring the observable. So I think you can use the same model typically.
Right, great. Okay, there's more questions coming in, but maybe I'll let you proceed for now and take those a little bit later. So great, we're having lots of discussion. So thank you guys. Keep posting the
no
questions.
problem. So feel free to ask any question. And actually, if we take a bit more time, I will skip probably one part of the talk, no problem. So let me go to probabilistic error cancellation. This is apparently a completely different technique, but as we are going to show, it can be applied in a very similar way as zero noise extrapolation. So probabilistic error cancellation is a technique to estimate ideal expectation values. So I assume that we want to measure the expectation value of the observable A after an ideal circuit U applied to an initial state rho 0. And the circuit is composed of T local gates, G1, G2, Gt. So unfortunately, we cannot apply these ideal gates because we have a noisy hardware. And so the first key idea of probabilistic error cancellation is to expand an ideal gate as a linear combination of noisy gates. So mathematically, you can think of G as a super operator acting on the space of density matrices. So basically, it's a big matrix, not so big, it's a gate. And it's unitary, but you have, in practice, you can implement non-unitary channels, which are again super operators acting on the space of density matrices. And if you take a linear combination of this, you can still recover the ideal operation. And the coefficients can be shown that they are real and normalized, and unfortunately, they are not positive. And so they cannot be considered as a probability distribution, and they are actually called a quasi-probability. So it's a quasi-probability distribution. And actually, the negativity of these coefficients determines how strong is the sampling overhead due to the application of error mitigation. If they were all positive, you could do this without any overhead at all. So if we now replace this expansion into the circuits, exactly, if we take the gates and we put in the expansion of the circuits, we get the ideal expectation value expressed as a linear combination of noisy expectation values, where it is important to notice that these expectation values can be measured. So they are expectation values evaluated with circuits that are composed only of implementable noisy operations. So this looks too good to be true, so we are basically canceling any type of noise. Unfortunately, the number of terms in this sum is exponentially large. And so the second main idea of PEC is that instead of measuring all of them, you can sample some of them in order to approximate this expression here. You can use Monte Carlo sampling. And so in practice, you need to measure a finite subset of the noisy observables. This is a very quick overview of PEC in theory. And let's see how it can be implemented in Mitiq. So even if the theory looks so different with respect to zero noise extrapolation, in practice, from the point of view of the workflow, it's exactly the same process. You get a quantum circuit from the user. You need to generate, in this case probabilistically, a large set of random circuits, actually not random, but related to the input. And you execute these circuits on the back end, you get the result, and you use this linear combination that I've shown you before, so the quasi-probability distribution, to recover the error-mitigated expectation value. So what is the key ingredient to apply this in Mitiq? The key ingredient is the operational representation class, which is an object that is designed exactly to represent this type of linear combination of noisy gates that produces an ideal gate. So for example, if we define the ideal operation Hadamard applied to qubit 0 with this Qiskit circuit, and if we assume that we have depolarizing noise on the device, you can easily obtain one of these operational representations that can be printed and basically you get exactly this type of expression, which you have the Hadamard gate expressed as a linear combination of noisy gates. So this is the way in which you can apply PEC. After you have these representations, you call the function execute with PEC, and you get directly the result that you want. And together with this, you also get all the additional data of the process that you can analyze, and if you want, you can also plot and so on. So this was an overview of PEC, and I think I will skip the Clifford part.
There was a question from Anna about how do you compute the Etus, the eta coefficients in the noisy observables here?
Yeah, that's a good point, because in principle, even these Etas are exponentially many of them. So you cannot compute all of them, but what you can do is that you can sample, let's see here, what you can, so maybe the question is, how can I build this representation, not how can I compute the Etus, right? So these representations can be built if we know the full tomography of the noisy operations, or at least if we have a guess for the noise model of the system. And because depending on this, you get different representations. And in Mitiq, we also have a function that, given the superoperators of the noisy operations, produces this quasi-distribution that gives you the ideal gate. It's a numerical optimization problem.
Could you tell us a little more about how, if you're familiar with that particular function, how or what that does or how it works?
Yeah, so it's basically you minimize. So it's a minimization problem. You have these matrices, which is given as a data input. They are superoperators. They are matrices. And also this one is a matrix. And these Etas are your optimization variables. And then you can ask, among all the possible variables that you can put here that gives you G, what is the optimal representation? So what is the optimal choice of this variable that minimize the negativity of this distribution? So basically that minimizes the one norm of this set of coefficients, such that you still need to impose this condition. And in practice, it's a semi-definite optimization problem.
See, so you need to give it the noisy gate GI on the one side, which has both the noise and like a CNOT gate, let's say. And then you also need to give it a basis of gates that you can apply, or what exactly
Exactly.
is the
Yes.
Mm-hmm.
It's a basis of gates that you can apply. Usually you have a guess for them. Sorry. Oh.
Yeah, so I mean, I guess one native basis would be the set of all single qubit product polys, right? So that would be like 4 to the power of 2n number of
No, yeah, but you don't have to to try all this. Yes, if you have usually you have a single qubit or a 2-qubit gate. So yeah, it's the usual trick is to apply the same gate followed by Pauli gates and all the combination of Pauli gates. Maybe I can show an example later. I have a notebook.
Great.
Okay. And so given that we are a bit late on the time, I will maybe skip Clifford data regression, which is also a nice technique, but I don't think I have time to show this. And I will also skip, maybe I will say something about this. So I would like to explain that Mitiq can be used to implement research ideas. So for example, in this paper, an adaptive zero noise extrapolation technique was proposed in a purely theoretical way. And just a few months later, we have been able to implement this in Mitiq by simply defining a new factory class and using a template class that we already have in Mitiq, which is adaptive factory. And by a few lines of code, we could have this technique implemented in Mitiq. And if you have some ideas to perform extrapolations, for example, feel free to contribute this as a new class in the Mitiq repository. Another technique which we tested using Mitiq, and we actually implemented all the simulations using Mitiq, is NEPEC, which is an extension of probabilistic error cancellation in which noise scaling is introduced as an additional degree of freedom. So in PEC, you execute a lot of circuits at the same level of the noise, while in zero noise extrapolation, you execute the same circuit at different levels of the noise. So what we propose in this recent work is that you could do both things simultaneously in order to get an extended basis of circuits that you could use to infer the ideal expectation value of interest. So if you're interested, you can see how this can be done. But the message here is that Mitiq can be used not only to implement state-of-the-art and well-established techniques, but you could use it as a research tool. And yeah, I think we have still maybe 20 minutes or 15 minutes. I can jump to the notebook unless there are questions on these slides.
Yeah, thanks for all the questions, folks. Feel free to post them in the, or if I missed your question, because there was kind of a onslaught of questions, which is fantastic. Feel free to repost them now or towards the end. And hopefully we'll get, maybe after you finish the talk, maybe we'll have a little time to finish the Clifford data regression.
Yeah, I will be happy, no problem. I just want to keep things on time. And so.
And I believe, folks, that if you want to follow along, we have a link posted in the chat to this notebook. Yes, we do. I'm going to repost it now. So you can, I think, go to GitHub and I suppose follow along. All right, Andrea, take it away.
Okay. I'm just trying to... Exactly. I want to... Oh, sorry. Yeah. So in this notebook, I just want to show how Mitiq can be used with Qiskit quantum programs. So these are the three main sections of the notebook. I will first show how to compute a noisy expectation value without mitigation, so without Mitiq at all. Then I will try to apply zero noise extrapolation. And finally, if we have time, probabilistic error cancellation. So if you're running the notebook, you first need to install Qiskit and Mitiq, which can be done by executing this code cell. We filter some warnings, and we just define the circuit of interest. In this case, since it's just an example, what we do, you don't have to look at the details of the code, but it's just a way to generate a randomized benchmarking circuit of 2000 gates, more or less, 2 qubit and single gates, and also 2 qubit gates. So it's a lot of control nodes, which are the most noisy gates of the circuit. So this circuit is very long, 2000 gates, and so we expect it to be sensitive to noise if we execute it on a noisy backend. And why we use randomized benchmarking circuit? Because they are built in such a way that the result, the ideal result, is the identity operation. So we know what is the final state in principle, which is the 0, 0 state. And so we can check if we are, how strong is the effect of the noise and how good is the effect of error mitigation. So first, let's try to execute the circuit with an ideal backend. So we initialize, we set the number of shots, 10 to the 5. We initialize a simulator. We append the measurements to the circuit, and we get the counts. And from the counts, we estimate the expectation value of an observable. In this case, the meaningful observable is the projector on the 0, 0 state, which for a randomized benchmarking circuit should be 1. And so if we run this cell, indeed we get 1, because there is no noise in the execution. So now, if we want to check what happens with noise, we just need to replace this ideal backend with a real backend, or at least with a simulation of a noisy backend. So we basically copy the same instructions, but instead of initializing the ideal backend, in this case, you could do the following. You could initialize a real IBM device if you have an IBM account, and if you want to run this on hardware. But I suggest you to first start with a simulator, because things are much easier. And in this case, we import from Qiskit a clone, a classical clone of the real device. It is called fake lim. And by the way, the device is a 4-qubit device where it is important that we are going to use just the first 2 qubits, because it's our randomized benchmarking circuit is a 2-qubit circuit. So apart from this, the code is exactly like before, and what we get is that the final expectation value is 0.75. So there is some fluctuations, but more or less that's the result. And it's not 1, exactly because of the noise. So the aim of, in this case of error mitigation, is to try to reduce the noise such that we get an expectation value which is closer to the ideal one, closer to 1. And so we can try to apply Mitiq, and in particular, zero noise extrapolation. So the first thing that you have to do if you want to apply Mitiq is to define an executor, which in the simplest scenario is just a function that takes as input a circuit and returns the expectation value that you want to compute. So in practice, what we need to do is exactly apply the operations that we defined before, the instruction to compute the expectation value and to wrap them into a function that is called executor. So we just copy exactly the same type of operations, and then you get this noisy expectation value, and you return it as a real number. So once you have this function, you can just run the same experiment as before, but now everything is wrapped inside this executor function. So the reason why we need this executor is that this is used by Mitiq as a black box in order to apply error mitigation techniques. So let me first show really the simplest way to apply error mitigation in a real computation, which is you can import Mitiq, and then you just decorate the executor with, in this case, a zero noise extrapolation decorator. And if you do this, sorry.
Yeah, I was going to ask you why there's two.
The name of the decorator is with the underdash. So if you do this, now you can still use the executor as before, but what happens is that zero noise extrapolation is applied under the hood. And as you can see, you get a better result, which is closer to 1. This is the first thing to notice. And the second thing to notice is that we are actually calling the experiment several times because we are applying zero noise extrapolation. So we are executing 3 different circuits with different depths, which are sensitive to different amount of noise, which are extrapolated by Mitiq. All this happens behind the scenes, so the user doesn't need to care about this. But on the other hand, sometimes you want to play with the details of the extrapolation, and so it is better to check what kind of options you can use.
Which type of extrapolation is, or how do you set the settings on extrapolation? Yeah.
Exactly. So the default one is Richardson extrapolation, and the scale factors are 1, 2, and 3. Just default choice of Mitiq, but you can change this. And I will show this exactly in the next slides, so in the next cells.
And this is global folding?
Well, actually, this is another way of doing exactly the same. Instead of decorating the executor, you can instead call execute with ZNE, and you get exactly the same computation. I'm not doing something different here. I'm just trying to quantify how much the error was reduced. But here it is, yes, the part in which you can choose the noise scaling method and the inference method. So all the noise scaling methods can be found, they are actually represented as functions that take a circuit and gives as output a noise scale circuit. So let's call this function a noise scaling function. And let's import one of these functions from Mitiq. For example, fold global is the one that I've shown you before in the talk. By the way, the default one in Mitiq is fold gates at random, which applies local folding to a random subset of gates. Now, just to change something, we pick fold global. And just to check if it is working well, we get a circuit, and we apply the function, and we get a new circuit with more gates, actually with more or less the double of the gates, because the scale factor is 2. If you take, I don't know, 1.7, approximately you get 1.7 more gates, and so on. That's the noise scaling method. What about the inference method? The default one is Richardson extrapolation. So it can be initialized as a factory object, which is, for example, where it is. Richard. Yes, Richardson factory, where you can set the scale factors as a list of numbers like 1, 2.7, 3, 5.3, just random numbers at the moment. And once you have this, you can call the function execute with zero noise extrapolation and pass this noise scaling method and extrapolation method as arguments. And what you get again is an extrapolation, which you can also analyze later by looking at the factory object, by looking at the data inside the factory object. For example, you can plot what is happening behind the scenes. For example, in this case, 4 noisy expectation values have been measured and Richardson extrapolation has been applied to get the zero noise limit. And equivalently, you could apply exponential extrapolation and so on. I think this concludes the zero noise extrapolation part. And before I go to PEC, I don't know if there are questions or otherwise I will proceed.
There are questions about PEC, so keep going.
Okay, good. So to apply PEC, we import the PEC module of Mitiq. And the first thing that we need to know about PEC is that in principle, you have to know the noise model of the system completely. So the full tomography of all the gate set that you are applying. However, a good approximation, not a bad approximation, but a very simple one to apply is to assume that first, the noisy gates are just the C0 gates. That's of course not true, but it's a first rough approximation. And secondly, we can also assume that noise acting on the C0 gate is depolarizing. This is definitely not true, but it's maybe the best, low-level approximation that you can apply. And what is still missing, even if you assume all these restrictive assumptions, we still don't know how strong is the error of the C0 gate. And so we have to guess it. And a good guess is basically to look at the device that you have. And sometimes this is reported. For example, the C0 error probability is given by this connection here. And you can also extract it in Python from the properties of the noisy backend. So in this case, we extract the gate error probability of the C0 gate between the qubits 0 and 1. And this is just a number that we can use as a very rough approximation of the noise acting on the C0 gate. And under all these assumptions, we can now build the optimal representation of the C0 gate as a linear combination of noisy gates. And this, in the case of depolarizing noise, is very easy. You can just use a built-in function from Mitiq and generate the operation representation. So you generate this object, which is the C0 rep variable, that is basically the Python object that represents this expression here. So you have the ideal operation, which is the C0 gate, which is equal to some coefficients times the noisy C0 gate minus some coefficients times the noisy C0 gate followed by a Pauli X, followed by Pauli Y, Pauli Z, and the same to the other qubit, and also 2 qubit Pauli errors applied after the C0 gate. This is the full quasi-probability representation of the C0 gate. under all the assumptions that we have seen before.
Yeah, I see, because you have a depolarizing noise, which is a form of a poly channel, and so you can decompose it this way. And if you had, if you didn't want to assume it's depolarizing, is there something you can do here, or?
Yes. So if you, well, you need, unless you know how to write down the quasi-probability distribution from theoretical arguments, maybe you have an analytical expression. For example, for amplitude damping, it is also known how to represent the gate. But in the most general scenario, you have only the noisy operator. So you have only the super operators of your gate set. So maybe you have a set of gates that you can apply with your hardware, and you have the super operators of those gates. And then what you can do, I won't do it now because it's a bit complicated, but you can import from Mitiq PEC representations, find, yes, optimal. I don't remember now. It's find optimal representation, something like this. I didn't get good suggestions here. But
I think you need a dot, yeah. That's okay, yeah, I guess.
Yeah, there is a function that basically, given the super operators of this, gives you the optimal representation.
Mm-hmm. Mm-hmm. And okay, I see. And it's on you to construct O sub a's?
The base, it's up to you, and usually, as I said before, a good guess is something like this, in which you replace the same gate followed by other local gates, and sometimes it is very useful to add also a reset gate, because for example, for the amplitude damping channel, it can be shown that the reset gate is necessary to get a good representation. But it's still, yeah, it's true. It's up to you to choose the basis. Okay. If you want, we can explore a bit more this, but otherwise I will just try to run PEC with this set of representations. Actually, it's just the representation of the CNOT gate. And to run PEC, we decide how many circuits we want to probabilistically generate, in this case 100 circuits, and we decide how many shots per circuit we want to use. And since we want to compare with the unmitigated case, we distribute all the shots budget that we have equally among the 100 circuits that we generate. And for doing this, we define a new executor with a reduced number of shots, basically, that we call PEC executor. And so once we have this, we simply call the function PEC.execute with PEC that takes as input the circuit, the executor, and the quasi-probability representations, and the number of samples. And once we get this, we can compare the mitigated error and with the PEC error. Hopefully we get a reduced error when we apply PEC. So as you can see, this is taking a bit of time because what Mitiq is doing under the hood is to sample each gate of the circuit according to the representations and producing 100 versions of probabilistic circuits that will be the starting point for the application of PEC. After the circuits are generated, they are executed by the backend. And what you can see is that each time you execute a circuit, you use some budget of your shots, and most of the times the number of gates is the same, which in practice it means that most of the time you execute your input circuit, so the original circuit. But sometimes you apply one of those noisy operations that we have seen before, which is a CNOT gate followed by some Pauli gates, which means that the number of gates is slightly larger. So that's a simple way to detect when the circuit is changed. And in principle, by taking an average of all these circuit executions according to the rules of PEC, you can get a better estimation of the expectation value. And indeed, in this case, the error is reduced by 98%. So even under these very strong assumptions on the noise model. So basically, this concludes the idea of PEC. And I don't know how we are with time. I don't want to exceed too much. Maybe I can stop here.
There was actually, the next question was exactly how do you implement, well, from Amin, can you comment later on whether one can use Mitiq to implement the noise agnostic PEC introduced in PRA 107 blah? I think this is your paper.
Good, that's exactly this section.
So why don't you?
The notebook. So I'm happy to reply to this because that's a very new idea and still experimental. We actually don't know how scalable it is and how it works, but let's try to apply it. So the idea of NEPEC is that instead of assuming a noise model, you can try to build an operation representation, basically a linear combination of gates that gives you the ideal gate that works even for different levels of the noise. So to do this, we define these two functions that actually we can skip because they are just details that are used to produce operation representations of this form. Let me show in a simple case. You decide a set of noise scale factors, for example, 1, 3, 5, and then you call this function represent operation with NEPEC. In this case, you want to represent the CNOT gate. And this is what you get. As you can see, it's very different from the representation that we had before. Before we had a CNOT gate written as a linear combination of a CNOT gate followed by Pauli operations. Here, instead, we are trying to express the ideal gate as a kind of Richardson extrapolation of the gate, evaluated at different level of noise. And in practice, how can we evaluate a gate at different levels of noise? Again, we can use unitary folding to scale the length of the circuit in order to have a larger effect of the noise. So in principle, this type of representation is exactly the same type of operations that you apply if you want to do zero noise extrapolation. You take a circuit, you scale it, and you take a linear combination of the results. The big difference here is that we are doing this locally at the level of an individual gate. And so we are actually, yes, representing an ideal superoperator as a linear combination of channels, of quantum channels. I think this is the key idea. So if you have questions about this, feel free to ask. Otherwise, we can check. Yeah.
Why would this particular basis be a good basis to represent the gate n as a linear combination of?
Exactly. So it's not maybe an optimal basis, but it's a way of expressing the ideal one as a linear combination of the same gate evaluated at different noise levels. And since it is based on an extrapolation, it works for different levels of the noise. So let's make a very simple example. Assume that you have no noise in the system. So zero noise. It means that this C0 gate is equal to a C0 gate because there is no noise, but also this one is equal to a C0 gate, and also this one is equal to a C0 gate because it's an odd number of gates. And so if you take now a linear combination of the same object, you get the ideal gate. So this representation works if you have zero noise in the system, but
So, 1/3, 1/3, 1/3.
Yeah, the choice of the coefficients, it depends on the scale factor. So if you have, for example, another scale factor here, 9, these coefficients will change, and they are exactly the same Richardson coefficients that you use to apply zero noise extrapolation. So you can think of this as extrapolating just a polynomial to the zero noise limit, but it's not a number, it's a gate. That's the key difference. We are not doing extrapolation of expectation values, but extrapolation of operators.
That's very interesting. So the 1.688 minus 0.75, those are the coefficients?
These are the coefficients, yes.
Mm-hmm.
These are just real numbers.
And how are they obtained again?
So they are exactly the same coefficient. They are obtained by this function, but I think I have to explain it. This is the function that you would use to extrapolate. Let me show this. To extrapolate here, this is Richardson extrapolation. So if you get 4 expectation values, in order to get the zero noise limit, you have to take a linear combination of these 4 expectation values. Basically, you fit a polynomial, and this number is a linear combination of this, this, and this, and this. This is called Richardson extrapolation. And now we take exactly the same coefficients because the coefficients depend only on the level of noise. That's an important aspect. It doesn't depend on the value of these expectation values. We take these coefficients and we use them to get the zero noise limit of the gate. So that's maybe not very clear. I think that the best way to understand this is to first understand how zero noise extrapolation works. And if one is convinced about how Richardson extrapolation works for expectation values, here you are essentially applying it for each matrix element of the superoperator.
And a quick question from the audience. So the results of noise agnostic PEC are biased. Is that right?
Yes. So this is an approximation of the ideal gate. It's not an exact decomposition. I agree, it's biased. But yeah, it's biased. But it's more robust to the ignorance of the noise model. That's the motivation behind it.
Sorry, what does more robust to the ignorance of the noise model behind it mean?
Yeah, so it means the following, that if you look, let me go back here. This representation that we used before is a representation that works only if the noise acting on these operations is a depolarizing noise of level C0 error probability. So there is a strong assumption on this one. In principle, it is exact, but as soon as the error model deviates from this, maybe the error probability is larger, maybe the noise is not depolarizing. If you have this representation is not true anymore, because if you execute this with a different backend, you don't get an exact identity anymore. So is this problem clear?
I think so. Yeah. I mean, here, if you if you let your coefficients be adjustable, you could do any poly noise model, but not anything larger than that.
Yeah, but it's not just this. It's that once you choose this, it means that you know how strong is the noise, right? This representation is a function of the noise model. And if you mischaracterize your noise model, this representation is not good, because you think the noise is something, but actually it's a bit more or a bit less or a bit different. On the other hand, since this is based on a extrapolation idea, it tends to work for different levels of the noise. And I don't know if this is convincing, but basically the coefficients of the Richardson extrapolation, maybe that's a way to explain it. These coefficients that you see here only depend on the noise scale factors that you choose. They are independent from the noise model. And of course, this is biased, but for example, if the noise is weak and if the noise is unknown, if you don't know how strong is the noise, these tend to be robust to mischaracterization of the noise model. Maybe I can also show a plot about this. I don't know. I don't think we have time. So there is a plot in the paper in which we show exactly this effect, this robustness to the mischaracterization of the noise.
Okay. Yeah. And is this a yes? I think maybe we see it at a high level, but might have to read the paper in more detail to understand exactly why this works.
Yeah, it's.
And I guess I should say how to what level of confidence has this been demonstrated to work or to work better? I think the question also actually asked from Amin was, can you compare this with typical zero noise extrapolation as well?
Yeah. So actually, we haven't done fully rigorous analysis of benchmarking different techniques. I think the only numerical experiments, have been done in the paper and in this notebook. So it's a very new technique, and we are looking forward to test this on hardware and to see which one is better and so on. In general, the motivation for this is that it's something intermediate between PEC and zero noise extrapolation. So zero noise extrapolation is biased, but can be very biased if the circuit, if the shape of the expectation value depends in a very nonlinear way on the noise, it can become very biased. PEC, on the opposite side, is unbiased, but it requires full knowledge of the noise model and so on. This is something intermediate. You try to do PEC without knowing too much about the noise model. So let me just mention another important point, which actually is the fact that if you want to use this representation, you have problems, because if you look at the one norm of this representation, it's quite large, it's 2.5, while the one norm of the previous representation is, where it is, here, 1.01. So it is extremely expensive to apply PEC using this representation here. So it turns out that the optimal way to reduce the norm and actually still to have good results is to have very large noise scale factors. So let's use just one and a very large number, like 101. This is a linear combination of the CNOT gate and a sequence of 100 CNOT gates, which in principle should generate more or less a random error, right?
Wait, I'm very confused though.
So basically, we are doing, it's like doing Richardson extrapolation with a scale factor of 101 for a single gate. It looks completely crazy, but the good thing of this is that you have a small one norm. And if you think about,
Can you motivate, so just intuitively, why does the one norm go down in this case?
Yeah, it's because you basically, it's like doing an extrapolation with a very large scale factor. And well, you have to look at the formula.
Yeah.
Usually these coefficients scale as 1 over the scale factor, something like this. And it's much, basically you can take a very small coefficient if you have a large scale factor.
Yeah, I guess my other just thinking is that usually with the Richardson extrapolation, at least with the pulse level extension, you usually work with pretty small scale factors also, because the noise swamps over your expectation values very quickly, and so you end up being in a noise floor, and then the inversion just goes wild due to the noise. So would that be this? I mean, it looks a little dangerous here to apply 101 gates, right?
I completely agree, but the point is here that we are doing something different. So this will happen with very low probability. So sometimes basically you add noise
That's
to the
true.
gate.
But that also means you need to sample a lot more, right? Because if you're not sampling this guy at all, then you're just applying the noisy gate to begin with.
That's true, but basically you need, since this gate is more or less 0.1, with 100 samples, you will sample at least 5 or 6 times. And if you increase the number of samples, of course, you cannot take here 1 million.
Yeah.
Otherwise, it's a problem. And also, it gives you a bad extrapolation. So there is a problem with this. I just want to give you a justification why it's not so crazy to do this. And it's to think about what happens if you apply this. Basically, you can think of applying a CNOT gate followed by a random Pauli error, because for sure, probably here, some Pauli error will happen. And so we are trying to induce artificially an error in the gate with very high probability, because we are applying 100 gates. And if you look at this representation that we had before, what we are doing is applying with some probability the CNOT gate, and with very small probability the CNOT gate followed by errors. So in some sense, it's good that we are inducing errors by applying many times the same gate, because this is what you need in order to apply PEC. You need to take a linear combination of the gate with the gate followed by errors.
And how do I know my bias here won't be like completely dangerously off?
That's true. On the other hand, the noise probability for a single gate, it's quite small compared to a full circuit. So that's why we can still apply 100, maybe that's too much, but maybe 50 gates and still have an effect of the noise which is not extremely large. So it's biased, it's more biased because we are taking a large scale factor, but maybe we can still extrapolate to a reasonable limit because the noise is very weak. It's just a single, we are considering just a circuit made of a single gate. But I agree, it's a problem. It's a very crude, rough approximation. Okay. So I have no idea of what will be the results here, but let's see what happens if we try to run PEC with this very strange representation. And again, as before, we are generating a lot of circuits under the hood. And hopefully, this will happen in a reasonable amount of time, yes.
And meanwhile, folks, please post any final questions you may have. I've taken a lot of questions during the talk, and I know we're running 25 minutes over, which is totally fine because here we really tried to get deep and far, but we will be wrapping up right after this awesome demo.
Yeah, good. So just to finish this, as you can see, in this case, it seems to work. I have to say that more or less I choose this scale factor, checking which one was working better and not. So if I take, I don't know, 71, also works, but I had to play a little bit with this before giving this talk, but there is a regime in which it works. So with this, I just want to go back here and just give a final slides for the conclusions. I think I skip reading this because we are very out of time. And thank you very much for the attention.
Yeah, thank you, folks, for thank you, Andrea, first of all, for the talk and the live demo. It's always very bold, do a live coding demo. So thank you. I know I enjoyed this a lot, and I have many more questions, and we'll check out the paper. With that, folks, I'd like to also thank you for the many questions during the talk. This is one of our longer talks, so exciting. Thank you a lot for tuning into all of the Qiskit live seminars this year. This is our final seminar of 2021. So have a nice break, but we will see you, I believe, next year in 2022, coming back. And with that, don't forget to subscribe to the YouTube channel, and we will see you after the new year. Thank you, Andrea, sorry. Thank you, everyone, and happy
Thank you,
holidays.
Zlatko. Thanks again. Bye-bye.